So coins flipped 18 times. What's the probability that exactly 12 are tails? So we know it's a 0.5 chance that we get tails. And since each time we flip the coin, one outcome is independent of the other, we can find out the probability of getting 12 tails by multiplying 0.5 to itself 12 times. Okay, so that right now just represents flipping a coin, just getting all tails. But we also have heads, which just happens to have the same probability. We have 6 heads, 12 tails. And if you compute this, it's very, very low. But in reality, getting 12 out of 18 to be tails, that doesn't seem that unlikely, right? It's because we also need to multiply this by the number of different ways it could happen. You could have tails, tails, heads, tails, 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 heads, 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 tails, 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 heads, heads, tails, tails, and I forget, lost count. That's one way of doing it, right? Or you could have all the heads happen at the beginning. That's one too many. Tails, 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 tails. Or you could have heads, tails, heads, tails. There's a lot of different ways that we could get 6 heads, 12 tails. So that's why we need this part of the binomial formula. In the formula, in the front, it'll say n factorial over p factorial n minus p. I think our book uses k. I don't remember. The letters don't really matter, as long as one letter stands for the number of different options. We're doing it 18 times, and we're choosing 12 out of 18 to be tails. And so this is the order. This is when the order matters. We multiply that to a probability p, to a k power, that's the number of successes, and then this is q, sometimes written, which is the same thing as 1 minus p, to the n minus k. So we've got p, we've got k, and then this is n minus k, right? Because n is 18, so 18 minus 12 gives us 6 up here. So we've got this part of the formula. This is what we're missing. And n is the total number of different times that we flip a coin, so that's 18 times. K is the number of successes, so tails is the item of interest here. So that's what we need to compute. So in the top, we're doing 18 times 17 times 16 times 15 times 14 times 13 times 12. And so we need a factorial here, okay? We're going to stop there because I'm going to cancel it out with the 12 factorial on the bottom. Okay? So 18 times 17 times 16 times 15 times 14 times 13, then the 12 factorials can cancel in the top and the bottom. And then we still have this out to the side. And actually, we can make that a lot easier, because if you have something of the same base multiplying to itself, the powers can add. And that's something we learned in algebra. That's a quick little trick to make that simpler. We can only do that on this problem because this is the only time the two probabilities are the same. So our computer couldn't handle that. But we can make that cancel out and make it a lot smaller. So in the top, we just need to do multiply those numbers, so we get something a little over 13 million. And in the bottom, we have, that's 18 minus 12 makes 6. That's 6 factorial. So that's 720 in the bottom. And this is still times 0.5 to the 18th power. So if we finish, divide that by 720, then times, here, I'm going to just keep that. I'm going to copy this to my clipboard because the next one's harder to type in. I'm going to type 0.5, raise it to the power of 18. It's going to be very small. Multiply that to the result I got out there, and finally we're done. What's the probability of getting exactly 12 tails? It's 0.0708. So that's 0.0708. Yeah, that's it. That's 4 decimals.